everyone, my name is Sam Grieggs, and today I'll be presenting the paleographer's eye ex machina, using computer vision to assist humanists in Scribal hand identification, along with my co-authors C. Henderson, Sebastian Sobecki, Alexandra Gillespie, and Walter Scheirer. Handwriting identification and retrieval is a well-explored area of biometrics. While handwriting itself is not a unique physical characteristic, it's heavily influenced by things like the size and shape of your hands and arms. So here are 3 samples of modern handwriting from 2 different writers from the CVL database. Are you able to find the odd man out? Modern handwriting is relatively easy to distinguish. In general, it's not inherently adversarial. This means that most writing is not made with the intention of trying to trick other people. In the cases where it is, few people are skilled enough to do it properly. That means that we can do really well on modern handwriting identification, and in fact we get pretty much perfect performance on modern data sets. Here I present some examples from the offices of the London Privy Seal. The office of the Privy Seal was an important part of the English legal tradition. They were professional scribes that would transcribe court orders and seal them to be delivered to the people who need to respond to them. They were essentially the printers of their day. As these scribes were professionals, they tried to make sure that their handwriting was as similar as possible. And 2 of these examples are from Thomas Hoccleve, who was not only a Privy Seal scribe, but also a key figure in 15th century Middle English literature, and he was significant for promoting Chaucer as the father of English literature specifically, and he was also one of the most important poets of the era in his own right. So the top 2 are from Hoccleve. This is a much tougher problem, specifically because the scribes deliberately write very similarly. At the same time, this is a problem of great interest to paleographers. These scribes would frequently be involved in literature as well, so by being able to identify their handwriting, that can tell us a lot about interactions between people like Chaucer and Hoccleve, and that's really important for understanding literary history. In general, paleographers are really good at identifying scribal handwriting. However, paleography has no agreed-on methodology or fixed criteria for the attribution of handwriting to a particular community, period, or scribe. Experts in the field will make attributions primarily based on their familiarity developed over a very long experience with a variety of scripts and individual scribal hands. In particular, paleographers focus on the aspect, which means the overall appearance of a scribe's hand. As you can imagine, this approach is inherently qualitative and subject to personal bias. In addition, the approach makes it difficult for paleographers to describe their results for publication. It just really looks like Hoccleve, may be true, but it does not sound very convincing. Paleographers therefore take pains to describe as thoroughly as possible particular features of a hand that seem most diagnostic. However, a lack of controlled vocabulary for this practice makes it difficult to compare one hand to another using these descriptors alone. Therefore, we propose a more quantitative approach. Now, computer vision offers solutions with spectacular performance on writer identification and retrieval benchmarks. But these methodologies have not been widely adopted by the paleography community because paleographers tend not to trust their results. Generally, they don't like that it just gives them a similarity score for an entire document. Furthermore, paleographers are typically not known for their technical acumen, and even relatively accessible computer vision research code ends up being quite inaccessible to them. Therefore, we built some software that paleographers are willing and able to use to help them build arguments for scribal hand identification. It has a graphical user interface and is distributed as a standalone executable for Windows, Linux, and Mac OS X with or without a GPU. It also allows the user to use our pre-trained model or define their own. And furthermore, our software gives visual feedback rather than a raw similarity score in order to make the software's comparisons more intuitive to a paleographer. This allows the user to analyze regions of the documents to identify what parts of the image are most persuasive to our model or whatever model they choose to use. Our software first breaks a document image into 64 by 64 patches. Then we run each one through some sort of model, which by default is a ResNet 50 that we trained specifically for this task, but can be replaced later by a user. And then we compare the resulting feature vector to a template using cosine similarity. The templates that we use are built from selected patches that are from known handwriting examples. And the way that we select these patches is that for each document, we take the top 100 orb features, run them through our model, and then aggregate them into one template that represents the author's hand. To aid in ease of use, we distribute a ResNet 50 that is trained on historical and modern text data sets using an angular margin loss similar to ArcFace. Specifically, our model was trained on the IAM handwriting database and the 2017 ICDAR historical identification challenge dataset. We also collected a number of other documents of interest, including some from the ledger of the Worshipful Company of the Scriveners. And this is a really kind of a unique data set because it actually has signatures from the scribes, whereas most of the time we do not have access to contemporary evidence of a scribe's hand. For the training process, we randomly select patches of the image that contain text and then augment them by replacing the paper background with random crops from ImageNet. And then we also color jitter the ink and this is to emphasize features that are related to text shapes rather than things like ink color or the type of paper that the document was written on. Our main objective was to build a tool that paleographers would use. So we tried to make this software as easy to use as possible. We designed it to use a graphical user interface that we built with PyWebKit, and it's also distributed as an executable rather than just Python scripts that are built for Windows, Mac, and Linux using PyInstaller. When the user loads in the software by clicking the icon, they are greeted with a screen that looks like this that prompts them to choose a template and a matching algorithm. Our ResNet 50 is the default, but we're working to implement more, and we've also built an interface that should make it straightforward to implement your own. From there, you can select Examine Image to go into our image examining tool. You can also, from this screen, build a new template from a selection of sample images of a known hand by clicking the Build Template button. The image examination screen, you can load in a document image and analyze it. It will break the image into patches and compare each one to the template, showing how similar each patch is to the reference template. The user can zoom and pan across a document, looking at the matching scores of individual patches, as well as the average scores from the whole document. We also did a case study to demonstrate one of the use cases for this tool. For this case study, we looked at the hand of Thomas Hoccleve, who was a highly productive and leading clerk of the Privy Seal, who also happens to be one of the most important 15th century English poets. So for our case study, we looked at 4 documents, which I show here. The first, from left to right, is Bodmore 48, a later 15th century manuscript of Chaucer's Canterbury Tales that was copied by a scribe 40 to 50 years after Hoccleve's death. Since Hoccleve was not alive when this document was produced, he could not have written it. But it is similar in content and style to Hoccleve's handwriting, so it offers a good sanity check for our tool. And you can see, looking at this example, much of the actual text region of the images scores very low similarity. The second document is from a copy of Hoccleve's Regiment of Princes, specifically British Library Manuscript Royal 17D18. There was some belief among scholars that this was a holograph, or the original copy written by Hoccleve himself. Ultimately, after much debate, the field seems to have settled on this not being written by Hoccleve. This, however, is an example that definitely fooled experts before, and our model matches this closer than Bodmore, but still, the text itself is generally very low. Our third document is from British Library Manuscript Harley 219, which contains many different texts and was written by several scribes, but this page that we have shown here, 134R, is uncontroversially attributed to Hoccleve, and our model matches most of the text quite strongly. Finally, our fourth and final example is from Cambridge Trinity College manuscript 0743 and is labeled here as TCC. This document had never been identified prior to Sebastian Sobecki, one of the paleographers on our team, finding it recently. He has independently verified it as Hoccleve writing in another publication, but we also showed this previously undiscovered example to our model, and it agrees that it was written by Hoccleve. Thanks for listening.